The sonar operator's hands are shaking, not from fear, from the realization that the faster they go, the more blind they become. K222 is breaking every speed record ever set by a submarine. 42 knots, 43. The hull screams through the Atlantic like a titanium banshee, and NATO hydrophones are lighting up from Greenland to Gibraltar. But inside the control room, the commander is staring at a dark sonar screen, watching his tactical advantage evaporate with every knot of speed they gain. Known as the Golden Fish for its astronomical cost, it was one of the most expensive projects in Soviet naval history. And somewhere in the design process, the engineers built something that could outrun any torpedo in the world, but couldn't hear it coming. The Americans gave it a code name, Papa. They tracked it effortlessly across 3,000 miles of open ocean. Not because Soviet technology failed, but because it succeeded in exactly the wrong way. What happens when your greatest achievement becomes your loudest vulnerability? When the thing that makes you fastest is the same thing that makes you a target?
Earlier that year, Captain Prozorov received his orders at the Northern Fleet headquarters in Severomorsk. K-222 was unlike any submarine he had commanded. The Papa-class prototype was built with a titanium hull and twin advanced pressurized water reactors designed to reach speeds no underwater vessel had ever achieved. His mission was simple in concept, but unprecedented in execution. Prove that speed could substitute for stealth in undersea warfare. The hull alone cost more than 100 conventional submarines. Engineers had welded titanium under inert gas atmospheres, developing entirely new techniques because no one had built a pressure hull from this metal before. Prozorov walked the length of the boat during his first inspection, running his hand along welds that represented a decade of metallurgical research and resources that staggered even senior admirals. Naval planners called K222 the Golden Fish, and not as a compliment. Construction costs had consumed resources equivalent to roughly 1% of the entire Soviet GDP. For that expenditure, the Navy could have built dozens of conventional submarines, each capable of combat deployment. Instead, they had one experimental vessel whose tactical value remained unproven. The titanium hull alone required industrial capacity that did not exist when the project began. Entire factories were retooled to produce the metal and develop welding techniques that could join it without contamination. Senior officers questioned whether a single prototype justified that investment. But the design promised something no other submarine could deliver: the ability to outrun NATO torpedoes and close engagement ranges before enemy ships could react. The twin reactors generated far more power than any conventional submarine design. The cooling system could absorb tremendous heat and transfer it efficiently to steam generators, driving turbines that turned the massive propellers. But the system imposed a critical constraint. The reactors required constant high-speed flow for cooling. Slowing below a minimum threshold allowed the coolant temperature to climb toward dangerous levels. The reactor crew chief explained the problem to Prozorov during the captain's first engineering briefing. Unlike some reactor designs that could idle quietly at low power, K222 systems demanded velocity. The submarine had to keep moving fast to stay cool. That engineering choice would shape every tactical decision Prozorov made. Standard Soviet submarine doctrine assumed boats would trade speed for silence. Captains trained to operate at slow speeds, minimizing noise while using passive sonar to detect enemy ships before being detected themselves. K222 inverted that logic entirely. The design bet everything on velocity. If the submarine could accelerate faster than NATO torpedoes and close engagement ranges before enemy destroyers could react, then acoustic stealth became secondary. Prozorov understood the theory, but he also recognized the gamble. Decades of doctrine, training, and tactics all assumed that silence was the submarine's primary weapon. Now he commanded a vessel designed to abandon that principle. The question was whether speed alone could substitute for the invisibility Soviet submariners had relied on since the Second World War. Initial sea trials revealed a critical flaw. Above 30 knots, the propellers began to cavitate. Water pressure at the blade tips dropped below the vapor point,
forming bubbles that collapse with shockwave intensity. Each bubble collapse generated noise loud enough to be detected hundreds of nautical miles away. The sonar officer reported the problem during the first high-speed run. He could hear the cavitation through the hull itself, a roaring hiss that drowned out every other sound. If the crew could hear it inside a titanium pressure hull, NATO hydrophones in the deep ocean would pick it up effortlessly. The engineering team was tasked with analyzing blade geometry and flow patterns, but the physics imposed hard limits. Moving that much mass through water at high speed would always generate noise. The cavitation noise was only part of the problem. At high speed, water turbulence over the hull and around the sonar domes generated flow noise that drowned out the submarine's hydrophones. According to technical accounts from the trials, at 15 knots, operators could detect surface ships at ranges exceeding 20 nautical miles. At 30 knots, effective range reportedly dropped below 5 miles. Above 35 knots, the screen went nearly blank. Flow noise overwhelmed every frequency band the equipment could monitor. K-222 became effectively deaf at the speeds it was designed to reach. Soviet doctrine depended on submarines detecting enemy ships before being detected themselves. But K-222 inverted this advantage. NATO could hear the submarine long before its crew heard any threat. Intelligence reports confirmed the worst fears of Soviet naval analysts. NATO hydrophone networks had tracked K-222 during every high-speed trial. The SOSIS arrays deployed across the Atlantic could detect cavitation noise at ranges exceeding 200 nautical miles. The submarine's acoustic signature was louder than any other vessel in the Soviet fleet, and possibly louder than any submarine ever built. Soviet officials reviewed the intercept data during briefings at fleet headquarters. Analysts overlaid K-222's trial routes with estimated NATO detection ranges. The circles were enormous. Every time the submarine ran fast, it broadcast its position across entire ocean basins. The Golden Fish could outrun torpedoes, but it could never hide from the ships launching them. Engineering teams attempted to redesign the propeller blades to reduce cavitation. They tested alternative geometries, blade counts, and pitch angles. Each modification reduced noise slightly, but never enough to matter. The fundamental problem was physics, not engineering. At 40 knots, blade tip speeds approached the limits where water could remain liquid under reduced pressure. Cavitation was not a design flaw. It was a consequence of the speed K-222 was built to achieve. According to accounts from trial participants, the dilemma became clear. They could reduce cavitation by slowing down, but that defeated the entire purpose of the vessel. Or they could accept the noise and hope speed alone would compensate. There was no third option hidden in better blade geometry. Prozorov convened his senior officers to assess the tactical situation. The weapons officer began with what seemed like good news. K-222 could accelerate to engagement range faster than any NATO destroyer could react. But then came the problem. The cavitation noise announced the submarine's approach long before it reached weapons range. Enemy ships would have time to deploy countermeasures, launch torpedoes, and maneuver defensively. The sonar officer interrupted with another concern. Flow noise prevented them from detecting those threats above 35 knots. And slowing down presented its own complications. Though unlike the later Alpha-class submarines with their temperamental liquid metal reactors, K-222's pressurized water reactors were more forgiving at reduced speeds. One officer posed the question everyone was thinking. Had they built the fastest submarine in the world, only to become the loudest target in the ocean? But another countered, what if speed was enough? What if they could simply outrun incoming torpedoes before enemy ships even completed their firing solutions? The room fell silent. They had the capability to reach engagement range faster than any NATO destroyer could react. The real question was whether that advantage could overcome the tactical limitations. No one had an answer yet. Orders arrived from Moscow in early December. Fleet Command directed Prozorov to push K-222 to maximum velocity and document the speed record. The directive emphasized proving Soviet engineering superiority, regardless of tactical noise concerns. Senior planners needed data showing the submarine could reach speeds no Western vessel could match. Prozorov read the orders twice. They acknowledged the acoustic signature problem, but framed the record attempt as a demonstration of technological capability, not operational readiness. The Golden Fish would justify its cost by setting a mark no other nation could touch. Whether that speed had tactical value was a question for later analysis. Prozorov folded the orders and called his officers to the wardroom. They had their mission.
The commander gathered his crew in the torpedo room, the only space large enough to hold everyone. He explained the mission plainly. They would bring both reactors to full power and accelerate to maximum velocity. Hull stress models predicted safe operation, but no submarine had ever moved this fast underwater. The titanium hull had been designed for these forces, but design calculations were not the same as empirical proof. They would be testing the limits of material science, reactor control, and hydrodynamics simultaneously. Some engineers believed the extreme forces might cause irreparable damage to the hull, making repeated trials at this speed increasingly dangerous. The commander told his crew they were about to set a record that might stand for decades. Then he dismissed them to their stations. The reactor crew chief pulled Prozorov aside after the briefing. He wanted the captain to understand the cooling constraints one more time. Sustaining full power output required coolant flow rates at the edge of pump capacity. The pressurized water reactors would generate heat faster than any submarine power plant in service. If they had to throttle back suddenly, the cooling flow would drop and temperatures would climb. They needed to maintain speed once they started the run, because slowing meant risking dangerous thermal conditions. Prozorov asked how much margin they had. According to accounts from the trials, the reactor chief paused, then said maybe 30 seconds before temperatures reached critical levels. Prozorov nodded. 30 seconds would have to be enough. The sonar officer delivered the final piece of bad news. Above 35 knots, they'd be deaf. Flow noise would drown out every hydrophone. No obstacles, no enemy ships, no seafloor. If a NATO destroyer sat in their path, they wouldn't know until they could see it through the periscope. And incoming torpedoes? At 40 knots, an enemy weapon could close from behind and detonate before they heard a thing. According to accounts of the trials, Prozorov was informed that flow noise was physics, not an equipment problem. The faster they went, the more blind they became. Prozorov nodded once. They were out of options. It was time to run. The commander returned to the control room and studied the navigation charts one last time. The designated trial area was deep water in the testing ranges near the Northern Fleet's bases, positioned to minimize encounters with shipping traffic and known NATO surface patrols. They would have as much safety margin as Soviet waters could provide. He checked the chronometer. Time to begin. The commander turned to the reactor officer and gave the order. Bring both reactors to full power. Initiate the speed run. The reactor officer repeated the command and relayed it to the engineering spaces. Turbine noise climbed as steam flow increased. The deck vibrated underfoot. K-222 began to accelerate, and everyone aboard knew that for the next several minutes they would be pushing the machine and themselves to limits no one had tested before. The commander gripped the railing and watched the speedometer needle start to climb. The control room hums with tension as readings climb. Lead bismuth coolant, or so the legend goes, at 310 degrees and rising. Every knot of speed pushes more heat through the system. Inside the compartments, uranium atoms are splitting, releasing energy, and that energy has nowhere to go but into the liquid metal racing through the closed loop. The metal flashes water to high-pressure steam. The turbines scream. But, according to accounts from similar reactor designs, here's the trap. Lead bismuth only stays liquid above 125 degrees. Drop below that and it solidifies, freezes the entire loop, kills the reactor. The story goes that crews had to keep the flow fast, which meant they had to keep moving. Slowing down allegedly risked thermal imbalance. Stop entirely? The whole system could cascade into emergency shutdown, or worse, loss of cooling.
Whether this was the K-222's actual constraint or a conflation with later designs remains debated. But the principle was real. Some Soviet submarines were locked in a race against their own physics, where the only way forward seemed to be faster. The twin propellers spun faster as turbine power increased, each blade accelerating water backward to generate thrust. At high blade tip speeds, pressure on the trailing edge of each blade dropped below the vapor pressure of seawater. Water flashed into vapor, forming cavitation bubbles that grew and then collapsed in milliseconds as they moved into higher pressure zones. Each collapse released a shock wave, a tiny hammer blow that propagated through the water as sound. Multiply that process by thousands of bubbles per second across both propellers, and the result was a roaring acoustic signature louder than any mechanical source aboard the submarine. Cavitation noise radiated through the ocean as low-frequency sound, traveling hundreds of miles through the thermocline layers where sound waves bent and focused, carrying the submarine's position to every hydrophone in range. The low-frequency noise from cavitation traveled through a specific ocean layer called the SOFAR channel, a depth zone where temperature and pressure combined to bend sound waves horizontally, instead of letting them dissipate upward or downward. Sound trapped in this channel could propagate for hundreds of miles with minimal loss. NATO hydrophone arrays were positioned at SOFAR depths precisely to exploit this effect. Every submarine operating at high speed radiated noise into the channel, and sensitive microphones could detect that signature across entire ocean basins. K-222's cavitation was feeding sound directly into the most efficient acoustic transmission layer in the Atlantic. The submarine might as well have been broadcasting its position on open radio. Physics made stealth impossible at the speeds K-222 was designed to reach. At 40 knots, hydrodynamic pressure on the hull generated forces that pushed titanium toward its design limits. Water flowing past the submarine's streamlined shape created pressure differentials that tried to compress, bend, and twist the structure. Titanium could withstand those stresses if the welds held. Every joint in the pressure hull was a potential weak point. Welding titanium required inert gas atmospheres to prevent contamination, and even microscopic flaws could become crack initiation sites under repeated stress. Once a crack started, it propagated rapidly under cyclic loading. At depth, a hull breach meant catastrophic implosion. Water would crush the entire pressure hull in milliseconds, faster than anyone could react. The submarine would collapse into a compressed ball of metal, killing the crew instantly. K-222's hull had been built carefully, but it had never been tested at these speeds. Water turbulence over the hull and around the sonar domes generated broadband noise that overwhelmed the submarine's hydrophones. At 40 knots, turbulent flow created chaotic pressure fluctuations that the sonar system could not filter out. The operator heard only roaring static across every frequency band. He could not detect enemy vessels, incoming torpedoes, or the seafloor ahead. The submarine was racing blind through unknown waters. The intensity of the internal noise made it effectively impossible for the crew to monitor their own external acoustic signature accurately, leaving them uncertain whether NATO ships were tracking them. Flow noise was not a design flaw. It was an unavoidable consequence of moving that much mass through water at that speed. The faster they went, the more blind they became, and there was no technical solution that could restore hearing at these velocities. The speedometer climbed past 43 knots, faster than any submarine in history. Hull-mounted strain gauges transmitted data to the control room, showing stress levels approaching design limits, but still within predicted safe margins. Prozorov watched the numbers carefully. Every knot brought them closer to the record, but also closer to the edge of what the hull could endure. The reactor officer called out cooling flow rates. Pumps were running at maximum capacity, moving pressurized water through the reactor cores at rates designed to prevent overheating. Turbine noise filled the boat, a constant high-pitched whine that penetrated every compartment. The crew felt vibration through the deck plating. K-222 was pushing harder than any submarine had been pushed before, and everyone aboard knew they were seconds away from either triumph or catastrophe. The sonar operator reported complete acoustic blindness. Flow noise had rendered every hydrophone useless. His screen showed nothing but static. No surface contacts, no bottom contours, no acoustic bearings. K-222 was racing through unknown waters with no way to detect obstacles or threats. The weapons officer had no targeting data. If an enemy ship crossed their path, the first indication would be visual sighting or collision. Worse, they could not hear incoming torpedoes. A NATO weapon could be closing from astern, and they would not know until detonation. The captain understood the vulnerability, but the record attempt required maximum speed, and that meant accepting blindness. He ordered the crew to maintain course and reactor power. They were committed now. Slowing meant failure, and failure meant the golden fish would never justify its cost. The reactor crew chief reported cooling flow rates at absolute maximum. Pumps could not push coolant any faster. Temperatures were stable, but only because the submarine was maintaining high speed. Any reduction in velocity would drop cooling flow and temperatures would begin to climb. The thermal margin they relied on was gone. They were balancing reactor heat output against coolant flow rate with no buffer left. If something forced them to slow suddenly, a mechanical failure, an obstacle, an emergency maneuver, according to accounts from the trial, the crew believed they had perhaps 30 seconds before automatic scram would shut down the reactors to prevent meltdown. Prozorov absorbed the information without comment. Maintaining this velocity magnified every hull stress and propeller load, but slowing was not an option. They had come too far to abort now. The record was within reach. The speedometer needle touched 44.7 knots, the record. Prozorov announced it quietly, and the control room crew acknowledged without celebration. They had just pushed an underwater vessel faster than anyone in history, but the achievement felt hollow. The cavitation noise broadcasting their position across the Atlantic was louder than any submarine ever built. NATO hydrophones from Greenland to Gibraltar were tracking them effortlessly. K-222 had proven that extreme speed was possible, but also that it came at a cost no tactical doctrine could accept. Prozorov gave the order to throttle back the reactors. The turbine whine began to drop. Hull vibration decreased. As speed fell below 35 knots, flow noise subsided and the sonar operator began to see his screen clear. They were alone. No immediate threats. But the acoustic signature they had left behind was unmistakable. As the submarine slowed and sonar finally cleared, the acoustics officer reviewed the data recorded during the run. The signature was unmistakable. Cavitation noise had peaked at levels exceeding anything in the Soviet fleet database, and probably louder than any submarine NATO operated. The officer compiled a preliminary report estimating that K-222 would have been detectable at ranges exceeding 200 nautical miles during the high-speed run. Prozorov read the report in his cabin afterward. The numbers confirmed what everyone suspected. K-222 had set a speed record that might stand for decades, but in doing so had demonstrated that speed without stealth was tactically useless. The golden fish could outrun any torpedo, but it would never reach firing range without being detected and engaged first. The mission was complete, but the answers it provided were not the ones Moscow had hoped for. K-222 returned to the Northern Fleet Base with the underwater speed record intact. 44.7 knots, a mark that still stands more than 50 years later. But there was no champagne at Fleet Headquarters. The acoustic analysis came back first. Detection ranges exceeding 200 nautical miles, far beyond what any NATO torpedo needed to lock onto a target. Then came the tactical evaluation boards. Prozorov sat through every simulation. Every single one produced the same result. K-222 would be detected and engaged long before it could close to weapons range. The flow noise, that screaming that filled the hull at speed, it prevented the crew from hearing incoming threats until impact. Speed had proven insufficient to substitute for stealth. The Papa class had answered a question, but the answer was not what the designers had hoped to prove. Soviet Naval Command made their decision. The program
was over. Construction costs and noise signature together killed the Papa-class program. Building a second vessel would consume resources equivalent to dozens of conventional submarines, and for what tactical gain? The first prototype had proven that speed came at the cost of detectability. Naval planners concluded that those resources were better spent on quieter submarines that could actually hide from NATO hydrophones. K222 was relegated to trials and technology demonstration roles. The titanium hull and experimental reactor systems became test beds for technologies that might be adapted to future designs, but the speed over stealth concept was abandoned. Soviet submarine doctrine would double down on acoustic stealth, not velocity. The Golden Fish had justified its existence by teaching the Navy what not to build. That lesson alone was worth the investment, but it meant K222 would remain the only Papa class ever completed. K222 served for roughly 2 decades in limited roles. The submarine tested reactor systems, evaluated titanium hull performance at depth, and trained crews on high-speed operations. Historical records indicate it completed at least 1 operational patrol, but the noise signature and sonar blindness made sustained combat missions too risky. Instead, the Golden Fish became primarily a floating laboratory, proving that titanium hulls could survive deep dives and that high-output pressurized water reactors could achieve record-breaking speeds. Those lessons informed later Soviet submarine designs, even if the speed over stealth concept was abandoned. Engineers studied the hull welds, analyzed stress patterns, and refined welding techniques that eventually made titanium construction more affordable. K222's legacy was not its speed record, but the engineering knowledge extracted from 2 decades of trials. The submarine taught the Soviet Navy how to build better boats, even if it could never fight itself. The Golden Fish proved that undersea dominance depends on silence, not velocity. Soviet and later Russian submarine doctrine shifted decisively toward acoustic stealth. Engineers focused on quieting propellers, isolating machinery from hull structures, and coating hulls with sound-absorbing materials. Resources that might have built more Papa-class boats instead funded research into anechoic tiles, pump jet propulsion, and advanced reactor cooling systems that allowed slow, quiet operations. The speed record K222 set became a historical footnote, a number that illustrated the limits of one design philosophy rather than a benchmark for future development. No nation has attempted to break that record because the trade-off is not worth making. In submarine warfare, the boat that cannot be heard wins, and K222 taught that lesson more clearly than any tactical manual could have written it. More than 50 years later, K222's speed record remains unbroken, 44.7 knots underwater. No submarine since has attempted to match it. The Golden Fish cost 1% of Soviet GDP and screamed across the Atlantic louder than any vessel ever built. The resources required to build a faster submarine would produce no operational advantage, and the noise signature would make it an easy target. The legacy of K222 lives on in a memorial, as her record-breaking hull was finally scrapped in 2010. Only her conning tower remains, preserved as a monument to engineering ambition and the hard limits physics imposes on submarine warfare. The engineering community understands what the Soviet Navy learned in 1969. In the darkness where she once sailed, the fastest submarine ever built rests silent at last. Not because she chose silence, but because silence chose the victor. The record stands, untouched, a finish line no one is racing toward.